Hi, welcome to the second video in Astrophysics series. My name is Hanish, and today we're doing one of astronomy's best magic tricks, measuring distance with nothing but light. No rulers, no tape measures, just photons and a little bit of geometry. The big idea is the cosmic distance ladder. We don't leap to the edge of the universe in one go. We climb rung by rung. By the end, you'll be able to compute a distance from brightness info and also understand what can go wrong and why calibration matters. Before we dive in, let me give you the map, because the distance ladder is basically a story, and the story has chapters. Chapter 1. Light spreads out. That gives us the inverse square law, the rule that tells you why things get dimmed fast enough in space. Chapter 2. Astronomers don't talk about brightness in the way normal people do. They use magnitudes, a logarithmic scale that turns huge brightness ratios into manageable numbers. Chapter 3. We connect what we observe to what the object actually is using the distance modulus, apparent magnitude versus absolute magnitude. Then we take a quick but crucial detour into spectra, because brightness depends on wavelength and temperature, and spectra are how we keep ourselves honest. And finally, we climb. Parallax is the geometric anchor, and Cepheid's variables are the first big standard candle rung that gets us out to other galaxies. And at the end, we'll do quick quiz problems, because I want you to leave this video able to compute something, not just nod along. Let's start with the physics engine, luminosity and flux. Let's first talk about two separate ideas, luminosity and flux. Luminosity, denoted by the letter L, is the total intrinsic power emitted by a star, while flux, denoted by the letter F, is the power per square meter that we receive, which is measured by the telescopes. The relation between flux and luminosity is given by this formula, F equals L over 4 pi d square, where F is flux, L is luminosity, and d is the distance between a power source, which in our case is a star, and an observer. Now let's read this plot, which demonstrates the inverse proportionality relation between flux and distance. This is geometry, where distance is labeled on the x-axis and flux on the y. Since the light spreads over a sphere with area 4 pi d square, so flux falls as luminosity gets distributed over area by the given relation, where 4 pi d square represents the area. If you analyze this graph carefully, it clearly shows a continuously decreasing curve as the distance increases, which means as the distance gets larger, received flux gets smaller. Therefore, star looks dimmer. Now look at the labeled points. Unit distance seems to have no effect on flux. But when the distance becomes twice the original distance, the star gets 4 times dimmer. That is why flux is 0.25. That one relationship is the engine behind brightness-based distances. Now, flux spans huge ranges, so astronomers use a compressed scale, magnitudes. Alright, magnitudes. This is the astronomer's way of making brightness manageable. Space gives us absurd brightness ranges. Some objects are so bright that they blow out your detector, and others are so faint you need long exposures just to notice they exist. If we used a normal linear scale, most graphs would be useless. So astronomy uses a logarithmic brightness scale, same idea as decibels in sound. Now look at the graph. On the x-axis, we have flux, meaning how much light reaches our telescope. and it's on a log scale, which means each step to the right is not a little more, it's usually 10 times more. On the y-axis, we have magnitude, the number astronomers use for brightness. Here's the strange part. The scale runs backwards. Brighter objects have smaller magnitudes. That's historical. People ranked stars by eye long before detectors, and the convention stuck. Now here's the rule that defines magnitudes. The change in magnitudes equals minus 2.5 times base 10 logarithm of the flux ratio. In other words, take the ratio flux 2 divided by flux 1, take the log base 10 of that ratio, and then multiply by minus 2.5. And that minus sign is everything. It means if the flux goes up, the magnitude number goes down, so the object is brighter. Let's use a graph to build intuition with two mentor rules. First, if one object gives you 10 times more flux, the magnitude changes by minus 2.5. So 10 times brighter in flux means 2.5 magnitudes brighter. Second, if one object gives you 100 times more flux, that's 10 squared. So the magnitude change is minus 5. So 5 magnitudes correspond to a factor of 100 in flux. That's a classic astronomy back pocket fact. Now one more important detail. Magnitudes are fundamentally about comparisons. There's a calibration constant in the full definition. But the beauty is that in most distance work, we care about differences, especially the difference between what we observe and what the object truly is. So now that we have a clean language for observed brightness, magnitudes, we are ready to connect what we observe, called apparent magnitude, to what the object intrinsically is, called absolute magnitude. And that bridge is the distance modulus. Now we are at the point where brightness turns into distance. On the slide, we are separating two magnitudes that sound similar but do totally different jobs. Apparent magnitude, denoted by lowercase m, is what we actually measure from Earth. How bright the object looks to us. Absolute magnitude, denoted by the uppercase M, is a standardized idea. It means how bright the object would look if we placed it at a fixed reference point of 10 parsecs. So M is basically an intrinsic brightness label. Now the big bridge is the distance modulus, which is just m minus m. That is the lowercase m, which is our apparent magnitude, minus the absolute magnitude. M minus m equals 5 times the base 10 logarithm of distance divided by 10 parsecs. So once you know apparent magnitude and you know absolute magnitude, distance is no longer a mystery. You can solve for it. Now look at this graph. It shows that this quantity grows slowly because it's logarithmic. So huge jumps in distance don't create insane numbers in magnitude space. That's why astronomers love this system. Key idea to remember. To use this, we must somehow know m, that is the absolute magnitude. That is the next question. How do we learn intrinsic brightness without already knowing distance? We start with the cleanest distance method we have, pure geometry. Parallax. This is rung one of the ladder. and it's the most honest one, geometry. As Earth moves around the Sun, a nearby star appears to shift slightly against the background of very distant stars. The tiny shift is the parallax angle. And the distance rule is beautifully simple. Here's how to say it. Distance in parsecs equals 1 divided by parallax in arcseconds. So you measure a tiny angle, flip it, and you get distance. No assumptions about luminosity, no guessing about star types, just geometry. Why is this rung 1? Because it calibrates everything. Once we know distances to nearby stars using parallax, we can determine their true intrinsic brightness. Then those objects become our calibration tools for methods that reach farther. Now here's the twist. When we measure brightness, we are measuring light in certain wavelengths. To interpret brightness properly, we need to understand what the star spectrum looks like. Now we take a quick but really important detour, spectra. Up to now, we've been talking about brightness like it's one number, but starlight isn't one number. It's spread across wavelengths. So before we talk about spectral lines, we need the baseline, what plain thermal light looks like. That baseline is blackbody radiation, thermal electromagnetic radiation from an object in or close to thermal equilibrium, where the spectrum's overall shape is determined mainly by temperature. Stars aren't perfect black bodies, but they're close enough that the smooth curve is a really good first model for the continuum, the underlying shape of starlight. Now look at the graph. Each curve is a different temperature. The feature to watch is the peak. As temperature increases, the peak shifts left towards shorter wavelengths, meaning bluer light. That's Wien's law. Said out loud, peak wavelength times temperature is roughly constant. That means hotter star means bluer peaks. And here's the extra punchline. Hotter stars don't just shift the peak, they also emit much more total energy overall. The total power per unit area rises like temperature to the fourth power. Why does this matter for distance? Because telescopes usually measure brightness through filters, visible, infrared, and so on. So you are only seeing a slice of this curve. Temperature tells you where the star is putting most of its energy, which helps you correct from brightness in a band to something closer to total brightness. This smooth blackbody curve is the continuum, but real stars have extra structure on top of it, spectral lines, which are the star's fingerprints. This slide is basically the star's barcode. Kirchhoff's laws tell us what kind of spectrum we see depending on the source. Hot and dense objects gives us a continuous spectrum, that smooth curve. Hot, thin gas give bright emission lines. Cool, thin gas in front of a hot source gives dark absorption lines. Now look at the figure. The dips and the spikes aren't decoration. They encode composition, temperature, density, and motion. Why is this in a distance ladder talk? Because brightness can be biased. Dust and chemical composition can affect the observed brightness, and spectral information is one of the tools we use to diagnose what's actually going on. Now that we have talked about how light is distributed across wavelength, let's talk about total light, the bolometric idea. Bolometric is a fancy word that means all wavelengths. Bolometric flux is the total energy per second per square meter that reaches us from the star across the entire spectrum. The way to say the equation is bolometric flux equals the integral of flux per wavelength over wavelengths, meaning add up the energy contribution from every wavelength. This figure reminds you of a practical reality. We usually don't measure the full spectrum perfectly. We measure in bands, filters, and then reconstruct total flux using corrections. Once we have turned flux into a total, astronomers do their favorite thing, convert it into a magnitude. Bolometric magnitude is the magnitude version of the total flux. Here's how to say it cleanly. Bolometric magnitude equals minus 2.5 times base 10 logarithm of bolometric flux plus a calibration constant. That constant is a 0 point, basically a bookkeeping convention. The point of this slide is not to worship the constant. The point is whether we talk in flux or in magnitudes. The latter always compares observed brightness to intrinsic brightness to infer distance. Now we are ready for one of the astronomy's most powerful standard candles, Cepheid variables. Cepheids are the stars that make the distance ladder feel like cheating. A cepheid is a pulsating star. Its outer layers expand and contract, so its brightness rises and falls in a stable pattern. Henrietta Leavitt discovered the key rule. The pulsation period tells you the intrinsic luminosity. Longer period means a genuinely brighter star. So here's the workflow, and it's beautifully mechanical. Observe the light curve and measure the period. Use the period luminosity relation to infer the star's absolute magnitude, its true brightness. Measure the star's apparent magnitude, and then use m minus m, which is the difference between your apparent and absolute magnitude, to compute distance. That is why Cepheids are rung 2. Parallax calibrates nearby Cepheids, which pins down the period luminosity relation. Then Cepheids let us measure distances to other galaxies where parallax is too tiny to detect. Now let's zoom out and see the latter as a whole system. This slide is the big picture. The latter is a chain of calibrated methods. We start with geometry, parallax, that gives us truth nearby. Then we use that truth to calibrate standard candles like Cepheids. Cepheids reach much farther into other galaxies. Then beyond that, astronomy uses additional rungs, often Type 1a supernova, to reach deep cosmic distances and eventually connects to the expansion of the universe. The key message: each rung depends on the previous rung, so uncertainties propagate. That is why astronomers obsess over systematics like dust extinction, crowding in images, metallicity effects, and calibration drift. Now let's ask the questions that take you from the formula user to measurement thinker. These are the kinds of questions that open the door to real astronomy. If dust makes stars dimmer, how do we distinguish far away from dusty? If parallax calibration shifts even slightly, how does that ripple through the entire ladder? If Cepheids in different environments behave slightly differently, what systematic bias does that create in distances? If you can reason about these, you're already thinking like someone who could do research. Okay, time to test your tools with quick quizzes. Quick check. No rushing, let the physics run. A star gets 3 times farther. Luminosity stays the same. What happens to flux? Pick your answer. You can pause the video here if you need some time to think. Answers will be revealed on the following slide. Flux falls with the square of distance. So tripling distance makes the flux 9 times smaller. That is why the distance is brutal. Even small increases in distance kill brightness fast. This one is straight distance modulus. You're given apparent magnitude and absolute magnitude. Compute m minus m and solve for distance. Solution to this one is, first we compute the distance modulus, m minus m, which we also denote as mu. Then set it equal to 5 times the base 10 log of distance over 10 parsecs and solve, which gives us d equals 100 parsecs. The key move, the logarithm turns into a power of 10. Once you spot that, the problem becomes simple. Cepheid's concept check. Cepheid A has a longer period than Cepheid B. Which one is intrinsically brighter? Leavitt law says longer period means higher intrinsic luminosity. So, Cepheid A is intrinsically brighter. Let's compress the whole story. Light spreads out. Flux drops as 1 over distance squared. Magnitudes are logarithms that make huge brightness ranges manageable. The distance modulus connects observed brightness to intrinsic brightness. Parallax anchors the latter with geometry. Spectra tells us how to interpret and correct brightness across wavelengths. Cepheids give intrinsic brightness from their pulsation period, extending distance to other galaxies. If you want the next quest after the video, learn the next rung. Type 1 is supernova, and then you run into one of modern cosmology's biggest puzzle: how precisely the universe is expanding. If you like this video and would like to watch more, subscribe my YouTube channel, The Dignified Professor, and stay tuned for the next video. Thank you.